Thank you, Mr. Ivers.
You're welcome. Okay, so as Mr. Mesco said, we wanted to just kind of take a different slant on this, and frequently it takes 2 or 3 or 4 times of looking at something like subnetting to kind of get it anyway. So, well, we're going to throw it at you 3 or 4 times, and maybe let me try it. And you heard what Mr. Hillard had to say about it the other night, and so I'll give you a little bit different slant on it. And like Mr. Mesco said, we're going to look at it today just from the purely math side of things, with very little reference to networks, okay? Maybe just a little bit. So, the underlying issue of everything about subnetting is in the word sub. What do we mean by subnetting? Okay? What that means is, in an address on a network, we have to break it into parts, and hopefully you got that the other night. The underlying thing is, we're going to take that address and break it into, and we're going to say this part of the address, it determines what network we're on, and this part of the address determines what computer or what host we're talking to, right? So that's the underlying concept, is we're going to take these numbers and break it into parts. Well, the problem is we need to know which part is network and which part is host or computer, right? That's what subnetting is all about. How much of it am I going to use for network and how much am I going to use for host? And we're going to look at it in something that probably makes a little more sense to you first and then relate it to that. So we'll come back to that whole concept. This, as you can see, does it say that somewhere on there, is a zip code map of the United States. If you look at that for just a couple of minutes, what can you tell me about a 5-digit zip code? Some of these have 3-digit parts up there, okay? So kind of ignore that. But look at the parts that just have 2 digits. You know, these parts like this. So what can you tell about that 5-digit zip code by looking at that map? What do the first 2 digits of a zip code tell you? They call them regions here. It tells you, so how do we know that? Well, we can kind of deduce it from looking at that map, right? So this is a good, more real world to most of us example of doing the same thing. A zip code, really, we don't know that. You know, most of us could pay very little attention to that. But in reality, the first 2 digits of a zip code tell you what region that mail's going to. The last 3 digits end up telling you which post office, right? Well, that's the same way that what we're going to look at, we're going to take part of it means this and part of it means this, but it all runs together as one big number, right? Okay, so let's, and in this case, the reason we know that, if I can pull up, we know that at this point for 2 reasons maybe. Number one is that we just looked at a map and kind of deduced that, but here is a website from the post office. What does it say right there? What do the zip code digits stand for? All right, and that's like basically what we just said, right? The first digit stands for one of the large regions, and then the next digit, and so on, right? Same concept. So this concept does apply in areas other than subnetting, is what I'm trying to get you to see. Okay, so if I can turn this off, then we'll get rid of this so I've got room to draw. Okay, so if we say, just forget all about binary for a few minutes, and I'm going to tell you that this is the address of something, you know, or whatever, you know, how we're going to identify things. Maybe it's offices in a large company or something. What if I told you that this is the region number and this is the particular office number? Kind of like zip codes, right? If I look at that, and this is normal decimal math, forget about binary for a few minutes, how many, this is regions and this is offices in those regions. How many offices can I have in each region and have a unique number for it?
Probably like 10, I think.
Not like 10, exactly 10, right? Because this number can be from 0 to 9 for a total of 10, right? And how many regions could I have? 100, exactly. 0 through 100. Or 0 through, you have to be careful of that. The largest that can be is 99, but that totals 100, right? Okay? Now, what if I said, well, you know, I've got some regions, I really only have about 20 regions, or let me back up. I really only have, say, 8 regions, so I really don't need a number quite that big. And I've got, some of my regions have more than 10 offices in them. How can I change my scheme here and fix that?
Use the first digit for your regions and the second and third for your offices.
Exactly. So instead of using that scheme, I would do this. Say this is regions, and this is offices. All right? So now what am I range? Now I have 0 to 99 offices, or 100 of them, but I only have 0 to 9 regions, or 10 of them. But that's okay, right? Does that not meet my requirements? That makes sense to us, right? Because it's in decimal, right? A lot more sense than talking about ones and zeros. We don't think very well in ones and zeros. Okay, questions about that? See, when you'll hear the term when you talk about subnetting, when you learn more about it later on, about borrowing digits. What did we do here? We said, you know, this is not enough, so I'm going to borrow this digit and make it part of what I need and leave this guy with one less digit. So we borrowed a digit so I could have more of them. Okay? All right, so now let's talk a little binary. So if, you know, what does an internet address look like? 4 octets, right? I'll just write an example one up here just so we have, and you've seen this address 100 times already. And what does a subnet mask look like? And I'm trying desperately not to talk too much about networks, but you almost have to. All right, so this is made up of 4 octets. But what are each one of those really made up of? These are decimal representations of what? Of binary numbers. So 255 really represents what?
8 bits or 1 byte.
All ones, right? And this should be, for you guys in your computer math class, should be, I think, refresher for you at this point. Why does that equal 255? Because this is 1, 2, 4, 8, 16, 32, 64, and 128. Each one of them represents that weight in decimal, and if I total these all up, it equals 255, right? All right, so we're going to take, instead of looking at this whole big 32 bits across all 4 octets, we're going to look at just one piece of one of them. So instead of looking at 8 bits even, we're just going to start out with like 3. All right? Remember up here a minute ago, we had 3 9s. Now we've got 3 1s. What's the max, what's the only values those places can have? 0 and 1, right? That's it. Not 0 through 9 like we had a minute ago. So if I said in my example again that I had, these are my offices and these are my regions, how many offices can I have in each region? 2, right? And what are they? Office 0 and 1, right? So this can be 0 through 1 for a total of 2. And what can this be?
4.
How many?
4.
4, right? Why? Because what are the combinations of 2 binary bits? It can both be 0, 0, 1, 1, 0, or 1, 1. Those are the only possible 4 combinations of 2 binary bits for a total of 4, right? So you can have 0, 0 through 1, 1, which is 4. How else do we know that that's 4? You know, I know it here because we listed the unique possibilities out and can't count them. It's 4. Anybody know, how else can we know that that would be 4? 2 bits.
2 1s, so there could be 2 zeros too.
Okay, right, now that's what, we know it like this. But what if that was 20 digits? Or 20 binary bits? Would I want to have to go through this for all those possible combinations? Mathematically, how can I know that?
Exponent.
Yeah, think exponents.
Basically, that first one, that's 2 to the power of 0 or 1, and the second one's 2 to the power of 1 or 2, so. Oh man, guys, I had my
You
head.
got exponentially screwed up.
Yeah, I had it.
It's 2 squared, right? 2 squared is 4. But why is it 2 squared? Because we have 2 bits, and each one of them has 2 possible values. Right? But that makes sense to everybody? So no matter how many bits I have, if it's 2 bits, 3 bits, 8 bits, 10 bits, it's that number squared tells you how many possible combinations there are of that number of bits. So let's take it one further.
Actually, it's the other way. It's 2 to that power. I think you
Yeah, you're right.
switch the base
You're
and
right,
the
it is. I may have
exponent.
said that backwards, yeah. All right, we're gonna prove that here in just a minute.
Yeah, I think we're going to go that direction.
Yeah, we're gonna go that way right now. All right, so let's say that instead of having just 3 bits, I have 4, and we'll stick with this setup. How many possible offices do I have now?
2 to the 1,
Still just 2, right? 2 to the first power,
1 bit.
1 bit, yeah, you're right. And how many here? Well, let's list them this way first. So if I have 3 bits now, I better start like this. Is that all the possible combinations of 3 bits?
Yep.
Trust me, it's right. I've been doing it for too long. To be able to count in binary takes practice. But that's about as far as I can go without stopping and thinking about it. All right, this is 0, 1, 2, 3, 4, 5, 6, 7. Hopefully, with practice, you get where you can see that pretty quickly. So is that all the possible combinations of those 3 bits? Yeah, it is. And how many are there? 0 through 7, so a total of 8. Is 2 to the third not 8? Right? So you see where we're going? No matter how many bits I'm using, I can take 2 and raise it to that power, which I said backwards a minute ago. And that tells us how many combinations there are. So we don't have to keep doing this thing, because that gets out of control if you got 20 bits up there. You're going to be here for a few days to get that all done, because the numbers get huge. Okay? All right, so let's back up to my original example here. We said we've got 1 bit and 2 bits. These are regions and these are offices, and we have 0 through 1 are a total of 2 offices, and 0, 0 through 1, 1 are a total of 4 regions, right? Everybody, that's where we were a minute ago, right? Now, what if I need more offices and fewer regions? Remember how we did that in Decimal? How did we do that? We borrowed a bit, right? Or we borrowed a digit. These are, we call them bits in binary, but it's a digit, just like it is in decimal. So how did we do that? We made this offices and this regions. So now how many offices can I have? 2 squared. You learn to start doing it the shortcut way. So I can have 4, and I have 1, or I'll get it right in a minute. 2 to the first is 2. Right? Makes sense? Everybody with me at this point? I've been talking that long, so. Okay? So, but that's just 3 bits. Let's look at a single octet now. And we're going to say how many, let's say, in a mass like this. Well, let me talk about this for a second, actually. Remember we looked at that map a minute ago, and we kind of deduced from looking at that map that the first 2 bits tell us, or the first 2 digits kind of tell us what part of the country we're in. And then we looked on that website, and it said the first digit means this, and the second digit. How do we know that? Because it said so, right? I mean, that's the answer to that question, because it said so. How do we know on a network address what parts mean what? What part means network and what part means host? This guy right here, the subnet mask. That's its purpose in life. It tells us everywhere there's a 1 means network. And everywhere there's a 0 means computer or host. Okay? How do we know in networking which part means network and which part means host? There's not some website that tells us that. There's not, I didn't tell you that. This thing tells you that. On
What
every,
is that called again, Mr. Evans?
this is called the subnet mask.
Would
Its
you-
whole purpose in life, its whole purpose in life was to tell you on any given computer which part of this address is network address and which part is host address. All right, so how does it do that? Well, let's look at just this very first octet out here. What is that octet in binary? Somebody tell me? It's 192. These bits are weighted like this, right? Oops. Yeah, that's right. All right, so what bits do I need set to have a 192? I need 128, and what do I have left over? 64, so I need that one. Do I need anything else? If I add these two up, that's 192, right? All right, so I don't need anything else. Okay, and keep in mind, we're looking at just this very far left part over here right now. So that's my address, and then what's my mask? It's all 1s, right? Right? Everybody understands that? This is 255 means all 1s. Then you've learned in this class, I think, about ANDing, right? What happens, let me erase this part just so it's not confusing us. What happens when I AND a 1 and a 0?
Either one. Or,
I'm sorry? Remember how an AND works? If this and this are 1s, then I get a 1. So what's the answer here?
0.
0, right? And it's going to be the same for all these. I just AND them. And what do I get down here? 1 and 1 is 1, 1 and 1 is 1. So what am I left with? 192. So that's how the combination of these two says, well, what we're trying to identify is this is my network. This is my mask. I combine those two to figure out what network am I going to. Where's my target network? Well, and actually, I said that slightly wrong. I combine the address that I want to go to with my mask to figure out if I'm on my network. That's the whole goal here, is to figure out, am I on my own little network here? Is it somebody on my network? Is it somebody on my block that I want to talk to? Or is it somebody on the other side of the world? That's what I'm trying to figure out. So all we've looked at so far is this first octet. And does this match up with my address? Yep. We're still in my address. All right, so let's look at the second one. What do I get? Oops, I didn't leave that there. What gives me a 168? Well, it's going to be less than 192, so I need a 128 and what? I can't remember these things. What bits do I need to get 128?
We need 40 more than
Yeah,
120.
I've got 128 and I need 40 more.
32 and 8.
32 and 8, exactly. So this is 128.64, so I need a 32. This is 16, and I need an 8. Right? So now, if I AND those all together, what am I going to get? I'm going to get 1, 0, 1, 0, 1, 0, 0, 0, which is same thing, 168. So, I should have written this up here. All right, here's where we're trying to go. And I'm sorry, I should have said that earlier. This is my address, my subnet mask, but here's where I'm trying to go. Okay? So now, we're looking at this with my subnet mask. I said that wrong earlier, I apologize. All right, so we looked at the first two quartets, let's look at the last one. Why did I erase that? All right, the last one, or the third one, it's all zeros, right? this third quartet, or octet. When I add that, what do I get?
Zero.
Well, it's 0 for my address, but remember, I'm looking at this address, so I did this wrong. I'm sorry, I'm not thinking clearly. That's where I'm trying to go. So I end my subnet mask with the target address where I'm trying to go, and what am I gonna get? If I end these all together, I'm gonna get 2, right? This one bit right here is the only one that ends up with a 1. And I don't care about the last one because that's my subnet mask says it's 0. I don't care about that part. So where's the target network address that I'm trying to go to? 192.168.2.0. If I did the same thing with my address, and that's what you have to do, is you do it with my address and then with the target address. If I did that same function with my address, what am I going to get? Right? Everybody see that? The only difference is, this is all going to be the same. Right? This is all going to be the same. It's not going to change until I get to this octet. Because mine and where I'm trying to go are different. And this is where, so now I've got network addresses. I know that this is my network address. This is the target network address. They're different. So I handle things differently. We're not going to go into that. That doesn't matter. We're just looking at the math at this point, hopefully. So, all right, so that was hopefully a simple example. Let's look at one more thing, and then I'll shut up and let you ask questions. What if I needed, how many, using this mask, 255, 255, 255, 0, that means I'm using the last 8 bits, remember, for a computer, and the first 24 for a network. How many possible computers can I have with 8 bits?
2 to the 8th,
2 to the 8th, right? And how many is it?
256.
2 to the 8th is 256, which is actually 0 to 255. And how many networks can I have? You don't know that off the top of your head? 2 to the 24th? It's much bigger than that.
2 to the 10th is 1,024.
Yeah. It's 16 million. 16 plus million. All right? So with this configuration, I can have 16 million networks, but on any one of those networks, I can only have up to 256 computers. So, what if I've got some corporate network and I've got 260 computers, and I want them all on the same network. What do I have to do? Remember what we did in Decimal? I gotta borrow a bit, right? Because if I borrow a bit, that gives me one more bit to play with, and that would change this to 2 to the 9th, and this to 2 to the 23rd. And then these numbers change, right? 2 to the 9th is 512, and 2 to the 23rd is 8 million something. 8 million plus. So what did that do? Now I can have up to as many as 512 computers on that network, but I can only have 8 million networks. Well, hopefully that's enough. All right, but how do I represent that in here, is the question. How do I represent that in my mask? This is the mask as we have it right now. So that tells me that these 8 bits was the original configuration we had up there. This represents 8 bits, right? And this represents 24. What would this number look like if I borrowed 1 bit from here and added it to that? Or, I'm going to use 1 bit out of here. What does my mask need to look like? That's the question. We've talked about all this to get to that.
But you can't go over the 255, right?
Right.
In that case, yeah, okay.
Can I go over 255?
But it's not be 254.1 if you just borrow one?
Well, it's in binary, you're borrowing 1.
Okay.
So it'd be, instead of 2
Well,
to
we're
the
not
8th,
actually borrowing 1, we're borrowing
a bit.
1 bit. But what you said is right. because why? Here's what these last two octets look like currently. But what I'm saying is I want to use this bit to be part of that now. I currently have 8 bits over there and 24 over here, right? I want to use this one to be part of that. So what do I have to do in my mask? Change it to a 0. Right? But then what does that do to this binary number right here? It's no longer 255. We took 1 away from it. Why 1? Because 1, 2, 4, 8, 16, 32, 64, 128. I took away its 1 bit, so I reduced it by 1. So this number is now 254. Okay? So if that were the case, if that was your obstacle, that you needed 1 more bit